So our last section of chapter 3 that we're going to cover is titled, was 3.6, and it's titled Inverse Trigonometric Functions and Their Derivatives. So right now we're going to do a little review of inverse trig functions, arc trig functions, arc sine, arc cosine, arc tangent, what they mean, and then we're going to move into some implicit derivation here. So you can see, obviously we see here from figure 1 that the sine function y equals the sine of x is not one-to-one. And we can see that by using the horizontal line test. But we do know that the function does happen to be one-to-one along this interval right here from negative pi over 2 to pi over 2. Now if we're thinking about this with respect to a unit circle, that is essentially representing the first quadrant and the fourth quadrant on a unit circle. Okay, so the inverse function of this restricted sine function f exists and is denoted by the inverse sine. So we say that by sine to the -1 or the arc sine. It is called the inverse sine function or the arc sine function, right? Since the definition of an inverse function says, and we state here that the inverse of f of x equals y, and therefore f of y equals x, then we have this, basically that the sine of -1, so the inverse sine is going to equal y, and the sine of y is going to equal x, and it's going to occur along this, this interval here, all right, where y is going to be between negative pi over 2 and pi over 2, right? Thus, if x is between -1 and 1, then we can say that the sine function, or the inverse sine, is between -2 pi and 2 pi, whose sine is in fact x. Okay, so just some examples here. We want to evaluate the sine, or the inverse sine of 1/2. And the tangent of the arc sine of 1/3. So first, the inverse sine of 1/2. We can say that the inverse sine of 1/2 is equal to pi over 6. And the reason we can say that is because the sine at pi over 6, so the sine of pi over 6 is 1/2. If you need help kind of remembering where this comes from, then it's important to pull up a unit circle. Take a look at the unit circle and it will help you to understand and see where those radian measures come from. Essentially, here we're writing it in terms of radians, which is what we'll use more often than not in calculus. But, it was also introduced using degrees before. Remember, pi over 6 would be 30 degrees, right? And pi over 6 lies between negative pi over 2 and pi over 2. Remember, pi over 2 is really 90 degrees, right? So we have negative 90 and 90, and this is representing our first and our fourth quadrant. Okay. Next here, let theta equal the arc sine of 1/3, so that the sine of theta equals 1/3. Then we can draw the right triangle. So basically, where does this triangle come from here? This is our understanding of, the 30, 60, 90 right triangle, okay? We can use the Pythagorean theorem here to figure out what the tangent of theta is going to equal. And when we do that, we can say that the tangent of the arc sine of 1/3 does in fact equal the tangent of theta, which is 1/2 root 2. Now we have some cancellation equations for inverse functions. That here in this particular case, and basically cancellation equations mean they kind of undo each other. In previous examples we might call them inverses essentially, but the inverse sine of the sine of x equals x. The sine of the inverse sine of x equals x. Okay. And notice that our domains here are a little bit different, right? In this particular case, it's between negative pi over 2 and pi over 2, first and second quadrant. But in the second case, we're between -1 and 1, okay? Now, okay, here. So the inverse sine function, right, has a domain. between -1 and 1, and a range of -pi/2, pi/2. And its graph is shown here, right? And obtain from that of the restricted sign function by reflecting it about the line y equals x. So remember, that's anytime we want to take the inverse of a function, we can just simply reflect it over that line y equals x. And we'll notice, you know, this is y equals the sine of x. If we want y equals the inverse sine of x, we just flip that, okay? And in other words, you know, I'm sorry I flew through this here, but that is in fact the arctan, right? So now in this case, going through this a little bit quickly, so just getting back to the slide we're supposed to be on, we can use implicit differentiation to find the derivative of the inverse sign, assuming that it is differentiable, okay? The differentiability is certainly plausible from its graph in figure 4. So let y equals the inverse sine of x, right? Then sine of y is going to equal x, okay? And that's our range, right? From -pi/2 to pi/2 on the y-axis. Differentiating sine y equals x implicitly with respect to x, we obtain this. So basically the cosine of y is going to be differentiated of dy dx, which equals 1. And therefore we can go ahead and isolate dy dx, which remember represents the slope of the tangent line. And when we do that, we get dy dx equals 1 over the cosine of x. Equals the cosine of x. Now the cosine is greater than or equal to 0 since, you know, we're dealing with this here, okay? So greater than or equal to 0 given this range. And so we can say the cosine of y is going to equal the square root of 1 minus the sine squared of y, which equals the square root of 1 minus x squared. Now remember, we are implicitly differentiating this, and that's where this is coming from. So therefore dy dx, remember, equals 1 over the cosine of y, or 1 over the square root of 1 minus x squared. And then we have another rule here, right? So the derivative of the inverse sine of x is going to equal 1 over the square root of 1 minus x squared, given the domain is between -1 and 1. Okay. And so, you know, basically what we're doing here in that previous example is we came out with what the derivative of the inverse sine is. Right? So now we could figure out what the derivative of the inverse cosine is in that same way. And when we do that, we can say that the derivative of the inverse cosine is now -1 over the square root of 1 minus x squared. So what we're doing here is we're really coming up with these rules. We are proving these rules. We are creating them by doing the calculus, the math, the algebra as we move through this, the trigonometry. And then we're getting these rules here. So again, these are rules that you want to be putting in your notes in preparation for that final examination, okay? So, you know, this is pretty much it in our conversation for the implicit differentiation of some inverse trig functions here. You know, we're going to move on to chapter 4 for the next section. Again, reach out if you have any thoughts, questions, or concerns.